Truly excited to be back again. I actually talk to you more about quantum mechanics, specifically looking at the Hermitian operator. We actually, from our previous video, focused on how we can actually recognize an Hermitian operator, and we actually define this from this particular formula, where if it obeys this particular presentation, where the integration coming from negative infinity to positive infinity of a particular, I will say, a well-behaved function f naught, where naught at the top here, or star, is actually representing the complex conjugate of that function, is presented with a particular operator, which is a, acting on another well-behaved function, which is g, and this is actually done with respect to tie, which could be any coordinate, either in 1 dimension, 2 dimensions, or 3 dimensions, and this is actually equal to the other side of the equation, where we rearrange our, I would say, specifically the well-behaved function, where now g is at the front, but then the complex conjugate is not only affecting our f but also affecting our operator. So in this case, we can now define our A to actually be an Hermitian operator, and this Hermitian operator will actually define our property, which is a physical property going from classical mechanics over to quantum mechanics. So in this particular case, we're going to build on this and be able in this video to dive into the proof that all eigenvalues, which is, I would say, represented as a n star here, of an Hermitian, are actually real numbers, which is just an. And where do we get an from? If you remember from our previous video, we looked at an with respect to defining our operator here to be acting on a function, and this produces an eigenvalue of that particular operator and reproducing our eigenfunction. So in here, we're going to be able to prove this particular part right here, and also see how we can be able to explain more about all eigenvalues of Hermitian's operator to be actually real numbers. So let's start off with this. From this particular formula, we can actually define, let's just say, our eigenfunction to be equal to phi n, and from there we can rewrite this particular formula to be a, which is our operator, written as phi n, and this is equals to a n phi n, where in this case we can define a to be a n, which are actually in this case real numbers. Now once we're able to do this, our next step is to be able to, you know what, let's actually define this particular phi n to be both equal to f, which are well-behaved functions, and also equals to g, which is also another well-behaved function. By that way, we can substitute those here into this equation and then see how we can actually go from there. So in this particular case, when we go in here and we expand on that, we'll be able to see that, oh, wait a minute, now our integration from negative to infinity to positive infinity is now acting on phi n, which is a complex conjugate here, and acting on our operator, or I would say now to be our Hermitian operator, and then this Hermitian operator is acting on this particular phi function with respect to tie, and this is equal to negative infinity to positive infinity, and this is rewritten in this particular case but done in the terms of, oh, our operator is going to be acting on our phi function but must also be actually a complex conjugate, so this affects anything that has I in it. But anyways, this is just by the root side, but let's continue from here, and we actually done or doing this with respect to tie. So from this particular case, we need to make another interesting notation in here, or substitution in here. So in this case, we're going to let A, which is our operator acting on phi, to be equal to an acting on phi, which is similar to what we had right here. And once we do this substitution into this equation, what we get now is our integration going from negative to infinity to positive infinity is going to be written as this time, and phi and complex conjugate, and this is written with respect to tie, and this is actually equal to the integration from negative infinity to positive infinity of the phi, and this is going to now be applied to the complex conjugate of both the real number and that of the, I would say, phi, and this is done with respect to tie. So in this case, we need to recognize something in here in this part where we actually see that by expanding our, I would say, complex conjugate on both the real number and that of our function, which is represented as phi, we can actually see that, hey, by that way we can actually arrive at an expansion that results in this particular result in the left side as what we got previously, while on the other side we actually showed the expansion on the right side of the integration, where we're going from negative infinity to positive infinity, where we're also applying that to our phi function applied to also our, I would say, complex conjugate of our real number and that of our phi, which is a function with respect to time. Now take note that an and an, I would say, complex conjugate is actually, or they are actually, real numbers, and since they are real numbers, then if you're tagging them, you're actually making them to be constants. And if you put a constant inside a particular integration, what that means is that you have to pull them out of the integration and actually treat them as constants, because integration doesn't act on a constant. So what that results in now is putting our constants out, which are an and the complex conjugate of an, which are real numbers, and we're going to rewrite now everything inside the integration with respect to phi, and phi in here is actually on both sides to be, you know, pre-equivalent in a way to each other, and seeing that we're able to isolate our an and an conjugate, we can now be able to see that the integrations on both sides, which is the left side here and on the right side there, are both the same. So by that way, the equation sign in the middle makes both sides to cancel out, and what that remains is our an, which is real numbers, are actually equal to the eigenvalue of a Hermitian operator, which is assigned as the conjugate of an. So all eigenvalues of Hermitian are actually real numbers, coming from the proof right there at the top, going from an star at the top to an or equal to an, and this is actually tagging various conditions, like giving various assumptions and conclusions that leads to actually arriving at our final solution, which is what we got right there. So all the same, thanks for following me through this, truly appreciate it. Hit a comment down below, let me hear your thoughts about this. By that way I can talk to you later. Stay smart and believe in yourself.